Hello, everyone. Now we are here to present the USTC-NELSLIP systems for the DIHARD 3 challenge. My name is Lei Sun. I will be with Maokui to bring you this talk together. This page shows all the participants in our team. The submitted system represents the joint efforts of everyone presented here. Before diving into the details, we first describe our motivations here. The pain point in DIHARD can be summarized into two categories. One is about the overlapped speech, including detection and assignment. This is the largest cause for performance degradation. The other one in DIHARD is about its diverse environments, including telephone, cafe, street, and other things like speech in the wild. Such complex data put forward a high demand to the generalization ability of diarization system. Hence, we mainly propose two ideas to address those problems, including iterative multi-stage strategy and domain-dependent processing methods. In this page, we illustrate the whole system design. For diarization, we use three different kinds of methods to solve the problem. The first one is a traditional clustering-based system. The second one is our proposed iterative speech separation-based system. The last one is the iterative target speaker VAD-based system. We also use several auxiliary techniques like audio domain classification, speech enhancement, overlap, and some ASR-related information to further enhance the overall performance. Note that the dotted lines in the figure are used selectively, depending on the domain classification results. Next, I may introduce Maokui to show the details of each part.
This is Maokui. Let me first introduce the audio domain classification part. Here we use ResNet-based network with 17 convolutional layers to classify 11 domains. The whole development set was divided into 10 parts, 9 parts for training, and the rest for testing. During testing, we use voting strategy to get sentence-level classification results. The proposed model achieved 100% accuracy on the development set, and we directly applied it on the evaluation set. The classification results were used as prior knowledge for subsequent domain-dependent processing. We employed a progressive multi-target network-based speech enhancement model as shown in the picture. PELPS1 refers to progressively enhanced low-power spectrogram at target layer 1, and the progressive increasing SNR between two adjacent targets was set to 10 dB. The enhanced speech was applied on restaurant domain with loud background noise, and it was also used for all domains of track 2 SAD. In this page, we introduce clustering-based diarization system, which acts as a basic system for our overall framework, as shown in the picture. This system mainly based on X-vector, PLDA, AHC, and VB clustering. The results on track 1 development set are shown in the table. We can see that given Oracle VAD, the miss value is the largest part in the whole DER, indicating that the traditional clustering-based diarization system cannot well handle overlapping speech. To get more accurate label of overlap regions, we solve speaker diarization via speech separation. We can see great similarities between the two tasks. Successful speech separation can yield good diarization result. Hence, we propose a novel speech separation-based framework for the speaker diarization task. As seen in the figure, the framework simply contains two parts, separation and detection. In separation part, original waveform is separated into two single speaker channels. The existing speech part will be captured by an SAD model in detection part. After combining all SAD results along the time axis, speaker derivation results were obtained where overlap regions were automatically labeled. However, currently, the generalization ability of speech separation model is not guaranteed. We show two real examples here, which are taken from CTS domain. The left is an example of successful separation. Two speakers of the speech are clearly separated. The overlap regions are actually labeled, while in the right, the separated results are messy. Speakers are not correctly separated. The blue box indicates those regions which should belong to speaker 2. To improve the generalization ability, we propose a multi-stage training method. In the first stage, we added a fine-tuning procedure using speaker price, which could be drawn from the classroom-based derivation system. Though the prior data are not pure and clean, it's still enough to do fine-tuning. After it, we directly use the fine-tuned model to separate the original recordings. What's more, we also found that using better price to simulate training data can significantly improve the separation model's performance. So we use the derivation results obtained from our separation-based method to return the separation model in second stage. Such an iterative processing method can further improve the derivation performance. Here is the experiment part. In pre-trained stage, we use the library speech dataset to simulate 250 hours data and train the convert translate as our pre-training model. In fine-tuning stage, we simulated 5,000 mixed audios for each session to train session-level models. The results of iterative speech separation-based derivation are shown in the table. Compared to the traditional method, ISS-based methods significantly improve derivation results on CTS domain of development set. We also utilize the TSVD-based method. Original TSVD take MFCC and I vectors of each speaker as inputs and predicts speech probabilities for all speakers simultaneously. This makes it possible to handle overlapping speech. With the well-matched training data on CHAM6, TSVD obtained great improvement compared with classroom-based derivation system. However, original TSVD can only process sessions with a fixed number of speakers. Obviously, it cannot be directly used in scenarios where the number of speakers is changing. Besides, TSVD does not perform well in the mismatch domain, indicating its poor generalization ability to diverse environments. This slide shows our strategy for dealing with a session where the number of speakers is not fixed. We first remain the original TSVD structure and set the number of speakers output to 8. Note that the session in DIHARD 3 have no more than 8 speakers in most cases. When the number of speakers was greater than 8, we randomly select 8 speakers for training and select 8 speakers with the longest voice for decoding. When the number of speakers was less than 8, we randomly picked speakers from the training set, and then marked these selected speakers with silence for training, and discard them after decoding. In order to solve the problem of mismatch between training and testing set, we proposed an iterative strategy for TSVD called iterative TSVD. Firstly, we decode the TSVD pre-trained model with I vectors extracted from the classroom-based derivation results. Then we removed overlapping segments detected by TSVD from classroom-based results and used the remaining non-overlapping segments to simulate multiple speaker dialogue data for TSVD fine-tuning. Finally, we use the I vectors extracted from the non-overlapping segments to decode the TSVD fine-tuned model and generate the iterative TSVD derivation results. Please note that we fine-tuned TSVD pre-trained model for each session. Here is the experiment details of iterative TSVD. The vector extractor was trained on voxelable 1 and 2, augmented with threefold speed perturbation. TSVD model was trained on real recording datasets, including switchboard 2, AMI meeting corpus, VoxConverse development set, and simulated multiple speaker dialogues with neighbor speech. And we also simulate about 4 hours multiple speaker dialogues for each session to fine-tune. TSVD pre-trained model only performs better than classroom-based derivation on well-matched domain like CTS and meeting corresponding to switchboard and AMI M20 set. Iterative TSVD helps improve generalization ability on most domains except web video and restaurant, mainly due to the large number of overlapping speech and noisy environments. As I mentioned before, we got several derivation systems, including classroom-based derivation, iterative speech separation-based derivation, and iterative TSVD-based derivation with different priors. We first perform system fusion with the overlap of above results, and then use the results of audio domain classification. We choose the best system for each domain according to the development sets. We also detected laughter with ASR and assigned laughter segments to each neighborhood speaker. This gave a slight performance improvement. Here is the DER of each system on development and evaluation set of track 1. We achieved a huge improvement with the mentioned method, which helped us ranking first on both full and core set of track 1. For track 2, most sub-modules are the same with track 1, so we put more efforts on the SAD part. We employ 3 different networks for SAD, that is DN, CLDN, and TDN. All the 3 models were fine-tuned on enhanced development set and tested with enhanced evaluation speech. Finally, we voted from the 3 systems and got a fusion SAD results. Here is the DER of each system on evaluation of track 1 and track 2. Our system shows its effectiveness even without Oracle SAD, which helps us ranking first on both full and core sets of track 2.
Okay, in this page, on behalf of our whole team, we want to express our appreciation during our journey in speaker derivation. Thanks for people who hosting and inviting us to great JSOT workshops from 2017 to 2020. Thanks for all organizers and contributors in DIHARD Challenge series who provide a great platform. 2020 was a tough year. We wish all colleagues can stay healthy and happy in the future. Finally, we list some take-home message here. First, iterative multi-stage processing is important. Also, speech separation is an interesting and promising direction to help derivation task. Last, compared with using a unified method, domain-dependent strategy is very useful for data like DIHARD. Thanks.